Okay, so tomorrow you guys have a quiz on chapter 6. You'll see a bunch of normal model problems, and then you'll see some binomial problems, okay? And so today I will cover everything about the binomial. I feel like it's pretty straightforward, so we'll see. I'll try to make sure you guys all have a good grasp on the concept, but yes, you'll have a quiz. Make sure you bring your reference tables to section, okay? So, I'll write this quiz tomorrow. Okay, and bring your tables and calculator. Table and calculator. So if you've misplaced your reference table, your Z table, it is available for download in either week 5 or week 6. I think week 5 there's a PDF file that says Z table, and you can or reference tables or something. You can print that out. Okay, so make sure you bring that. Okay, and yes, it will cover normal model and binomial. And I think we've covered the normal model pretty thoroughly. You guys have had some homework problems regarding the normal model, and so today we'll cover the binomial. Okay, so binomial distribution. Okay, like the normal model, this is another theoretic distribution. Okay. And the idea behind a binomial distribution is that you repeat a random trial n times. Okay, so this is kind of the setup for the binomial, is you repeat a random trial n times. Okay. Every trial has only 2 outcomes. Okay. And in the literature, they're labeled success and failure. In English, we associate success with a good thing and failure with a bad thing. But these are just arbitrary labels. It should really just be something happened or it didn't happen, okay? But we call them success and failure. Success meaning something happened, something in particular happened, versus quote-unquote failure, which is that thing did not happen. Okay. Each trial is independent of each other. Meaning that what happened in one trial has no influence on what happens on the next trial. And then, and so a consequence of that would be that each trial has the same probability of success. Okay, and that probability is P. Okay, and what we are interested in is we are interested in seeing X successes. Okay, and I should write, and the order in which these, and the order does not matter. Okay, so this is the setup in which you will use a binomial distribution, and so this is all a little bit lofty, or just little, maybe. Let me put this in practical terms with some examples. Okay, examples of binomial. All right, here we'll say I flip a coin 15 times. Each flip has probability of heads equal to 0.5, and I'll ask, what is the probability the coin lands heads 9 times? Okay, and so in this case, this is a binomial, and let's try to identify our 3 letters, our n, our p, and our x. What is our n in this situation? 15. We're flipping the coin 15 times. What's my p? 0.5. And what is my x? 9. Okay? And in this case, the order doesn't matter. I don't care if it's the first 9 flips that have to be heads, or the last 9, or the first 3 and the last 6, or some other weird arrangement. It doesn't matter. It's just after I flip the coin 15 times, I need 9 heads. That's what we're talking about here. Okay, let me give you a few more examples, and just make sure you guys have this all written down. You guys are taking notes. Okay, another example. Okay, so probably one of the best shooters in basketball right now is Steph Curry, and he has approximately 92-93% free throw shooting average right now, I think, which is, if you don't know, that's very, very, very good if you're into basketball. Okay, so we'll say Steph Curry. He plays for the Oakland team, Golden State Warriors. Yep. Okay, we'll say he has we'll say a 93% free throw percentage. Okay, meaning that every time he shoots a free throw, this might not be entirely true, but we'll say every time he shoots a free throw, he has a 93% chance of making it. Okay, and we will assume each free throw is independent. Perhaps that may or may not be true, but for the sake of our math, we'll assume that it is. And we'll say in a game, he takes, I don't know, 11 free throws. Okay, and then so we'll ask, we could say, what is the probability he makes at least 10 free throws? Okay, and so in this problem, let's see if we can identify our n, our p, and our x. What is the n in this scenario? N is 11. He's taking 11 free throws in the game. What's our p? 0.93. And what is my x? X is 10 or 11. Okay, because when we're saying at least 10, this means he's going to make 10 or 11. So in this situation, we have an x for 10 and an x for 11. Okay, and we're going to have to do 2 calculations and combine those together for this. Okay, so the at least means 10 or 11. So we do 2 calculations. And add them together. Okay, so that's another example of a binomial problem. Okay, and then maybe just one more. Okay, we'll say a school has, we'll say, 600 students, and we'll say I don't know, this is some zombie situation. Okay, we'll say 4 students are infected with a mysterious disease. Okay, and then we'll say, we have a machine, or we have a test. We'll say we have a blood test that can detect the disease. With a probability we'll say 80%. Okay, so we'll give we will administer the test to everyone. We'll ask, what is the probability we detect the all 4 infected students? Okay. All right, and so in this situation, what is our n? See, I have deceived you. N is 4. Okay. N is 4. We are administering the test to all 600, but the probability of detection, this 80%, only applies to the people who actually are infected, right? Okay. So in this case, my n is 4. What is my p? My p is going to be 0.8. This is the probability of detection. And what is my x? My x is 4. Okay? So here it's 4 are actually infected, and we want to see if we can detect all 4. We don't know which ones they are, but there's only 4 that really actually count as far as having this probability go. Yeah, we have a question. What's that? No false positives. Yeah, we're going to just assume no false positives in this thing. Well, we could talk about false positives, but that just complicates things, okay? So, as far as binomial, we'll just say there's a probability of detection of 80%. There's 4 that we actually want to detect, and we want to make sure we detect all 4. And so in this case, my n is 4, and our x is also 4. Okay, is this all right? So these are all binomial situations, okay? In all of these, the order does not matter, okay? If I had phrased something and I said, if I change this, instead of what's the probability he makes at least 10 free throws, if I said, what's the probability Steph Curry makes the first 10 free throws and misses the last one, then that's no longer binomial, because in that case, the order does matter. So let me just kind of contrast this. So if the question says, what is the probability Steph makes the first 10 free throws and misses the last one, this is not binomial. The order matters, okay? Here, the order matters. Okay, and so we'll say if we say H will be hits the hits the free throw, meaning he makes it. And then M will be miss. Then the sequence has to be 10 H's and then a miss. Okay, this is the only sequence that satisfies this question. Okay, whereas if the order did not matter, then there's a bunch of other sequences that would satisfy, just making 10 free throws. Okay, so how would we answer this? We know how to answer this question. What do we do? If somebody asks, what's the probability of this? You would say what? You multiply the probabilities. Yeah, you would just multiply all of these probabilities together, right? You would just do 0.93 times 0.93 times 0.93 dot 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 times 0.93, and then what's the probability of a miss? 0.07, right? And so our result would be 0.93 raised to the 10 times 0.07. Is that okay? And that's what we would do. And this is not binomial. This is just you multiply the probabilities down the line. Okay? But this actually serves as kind of a basis on how we calculate binomials. Okay? The only difference between this question and a binomial is that in the binomial, the order does not matter. Okay? So let me just change our example to just something a little bit more manageable. Okay? All right, and so let's say I don't know, you have a biased coin. I don't know what that means, but well, we can imagine some biased coin where the probability of landing heads is not 0.5, but is somehow 0.7. Okay, so we'll say the probability of landing heads will be 0.7, and we'll say if it's not heads, that means tails, just to make our life easier. So that means the probability of tails would be what? 0.3, right? Okay, and we'll say we will flip the coin 4 times, and we want to know what is the probability the coin lands heads twice. Okay, so in our problem here, what is my n, what is my p, and what is my x? N is 4. I'm flipping the coin 4 times. P is 0.7. This is the probability of getting heads, and x is 2. I want to have the coin land heads 2 times. Okay. All right, so I'm going to list off just one arrangement, okay? So this is one possible arrangement. Is that it could go heads, heads, tails, tails, okay? All right, so what is the, let's do the probability calculation for this. So the probability calculation is going to be 0.7 times 0.7 times 0.3 times 0.3. This is the probability of this exact sequence. So this is going to be 0.7 squared times 0.3 squared. This is the probability of this exact sequence. Okay. All right. What's another possible sequence? I can go heads, tails, heads, tails. This is another possibility. Okay, and the so I'll do another arrangement. All right, and the probability for this one is 0.7 times 0.3 times 0.7 times 0.3. Okay. And when I do this one, if I combine the 0.7s together, I still get 0.7 squared times 0.3 squared. Is that all right? Okay, and then here, I'll list off a few more arrangements. I'll have heads, tails, tails, heads. And what is the probability of this one going to be also? It's going to be the same, right? Because we've got 2 heads and we've got 2 tails. So this probability will also be 0.7 squared times 0.3 squared. Okay, and let me just list off all of these other arrangements. We've got tails, heads, heads, tails, and tails, heads, tails, heads, and tails, tails, heads, heads. Okay, and every one of these arrangements has the exact same probability. Every one of these arrangements have 2 heads and 2 tails, and so their probability is going to be 0.7 squared times 0.3 squared. Okay, so all 6 arrangements have the same probability, which is going to be 0.7 squared times 0.3 squared. Okay? And so the total probability for all 6 arrangements is just going to be 6 times 0.7 squared times 0.3 squared. Does that make sense? So the probability of getting 2 heads is going to equal we combine all of these, and it's just going to be 6 times 0.7 squared times 0.3 squared. Okay, does that make sense to everybody? Everyone's good so far? Okay, so let me just give you a quick question here. All right, so we'll say we're going to do the biased coin, and we'll say probability of heads is going to be 0.7. Okay, and this time I will flip the coin 5 times. Okay, and I'm not expecting you to list off all of the arrangements. Okay, I'm going to flip the coin 5 times, and I'll say I'm going to ask, what is the probability of getting 3 heads? Okay, and then I will just say, let me just do a quick calculation here. Is that there are 10 possible arrangements, okay? There are 10 arrangements of getting 3 heads in 5 flips. Okay, and so your answer choices will be, I got to think of some good all right, so we'll have 0.7, Okay, so I didn't do any actual calculations, but I've just, oops, sorry, let me get this going here. Okay, so I've just put them all kind of symbolically what we have. Okay, if you want to discuss with your neighbors what you think the correct answer is, go ahead and do that. All right, we'll say 10 more seconds here. Okay, I'm going to go ahead and click stop, and let's take a look here. Okay, that is the correct answer. We have a few people who made a mistake. So let's talk about how this works. Okay, so we're flipping the coin 5 times, and we need to get 3 heads, right? So getting 3 heads means how many tails are we going to get? Which means we will get, so we must get 2 tails. We must also get 2 tails. If we have 3 heads, we're going to get 2 tails. So one possible arrangement is we're going to have heads, 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 tails, tails. Okay, that's one possible arrangement. And what is the probability of this arrangement? Well, it's going to be 0.7 times 0.7 times 0.7 times 0.3 times 0.3. So this becomes 0.7 cubed, or 0.7 to the third, times 0.3 squared, right? So that's what we have, 0.7 to the third and 0.3 squared, okay? So that's one arrangement, and over here I said there are 10 possible arrangements, and so, you know, there could be, you know, heads, heads, tails, heads, tails, or something like that, and that's, you know, and there's going to be 9 more arrangements, okay? So a total of 10 arrangements, and every single one of these arrangements are going to have 3 heads and 2 tails, and therefore the probability of every single one will be 0.7 to the third times 0.3 squared. Okay, so the total probability, so all 10 arrangements have the same probability, which is going to be 0.7 to the third times 0.3 squared. And so because we have 10 of them, we're just going to multiply 10 times this answer, 0.7 to the third times 0.3 squared. Okay, and therefore our answer is D. Okay, is this okay? All right, so how do I know that there are 10 arrangements of getting 3 heads and 5 flips? Okay, so how do we figure out the number of arrangements? Well, the number of arrangements is going to be determined by this thing called n choose k, or n choose x. All right, so okay, it's called n choose x, also written as ncx, or written this way. So if you see parentheses where one number is written above the other, they are all saying the same thing, n choose x. Okay, and the formula for this, and I think in most mathematical textbooks it's written this way, but for whatever reason, you know, we often write it out this way. Okay, so the formula for this is n factorial divided by x factorial, and then we say, well, there's going to be 2 terms on the bottom, and the 2 things have to add up to n, so we do n minus x factorial. Okay, that's what we have. Okay, now it's like, well, I don't want to do this. All right, n factorial, if you don't know, is where you go, you know, n factorial is equal to 1 times 2 times 3 times all the way up to times n. Okay, that's what n factorial is. Now, if you don't have a graphing calculator, or not graphing, if you don't have a scientific calculator, you would have to use this. And this is why I highly recommend that you get yourself a scientific calculator, because there's a good chance that somewhere on your calculator you'll have a little button that says NCR. If you have a Casio, it's generally above your division key. There's a little NCR button, okay? And so I could do something like 5 shift divide key 2, and then I see 5C2 for 5 choose 2, and that will, or I'm sorry, the last one I said 5 choose 3, which is 5 flips, and I want to choose, so 3 of them are heads. I do 5 choose 3 and this says, well, there's 10 arrangements there, okay? So on your calculator, you might see there might be an NCR button, okay? Look for an NCR button on your calculator. Let's see. If you have a TI, you might have either a math or a probability button, okay? Or you might hit math and there's a probability menu somewhere, okay? And inside, once you hit your probability button or get to your probability menu, you'll probably see an NCR option there, okay? And then you'd probably do something like 5 NCR 3 is 10, okay? Or, so for example, if I said, I'm going to flip the coin 10 times, 10 flips, and I want 5 heads, the calculation we would do there would be 10 choose 5. Okay, and this would be too much trouble to try to list this all out, and the answer there is going to be 252. Okay, so now's a good time to kind of make sure you can use your calculator. You do 10 choose 5, and we'll list off. We do that and I get 252. Is everybody able to use their calculator okay? Kinda, maybe? So look for either a math or PRB button, and after you hit that, you might find somewhere in the menu NCR. If you have like an older TI, like a TI, I don't know, a 30 or something, you're gonna have to kind of like look on the inside of your calculator cover, and there's like a little paper in there, and I think one of them will say like combinations and talk about how to do NCR. It might be everyone's calculator is a little bit different, but you might see a NCR and choose R and choose X button. Yes, question.
So on the calculator, 5 is N and 3 is R.
Yes. So the N is the bigger number. It's always going to be X, or the R is always smaller than the N. Okay, smaller than or equal to. Okay. Is this okay with everybody? Yeah, I don't think I need to explain this entire thing here. Okay. All right. So let's try a problem out. Okay. So we'll go back to Steph Curry's free throws. Okay. All right. So we'll say Steph Curry takes 11 free throws. Okay. He has a 93% free throw percentage. And we're going to ask, what is the probability he makes at least 10 free throws? Okay, so the calculations, you'll have to do a few calculations here, and I'll make a question out of this, but I have to do the calculations myself and figure out the answer first. Okay, so again, the key here is that it says at least 10. Okay, and if you need to talk to your neighbor or work together with your neighbor, you are more than encouraged to do so. So I'll let the clock run for a few moments here. So get your clicks in. So we'll hit. Okay, I'm gonna hit stop, and let's see. Okay, yeah, for the most part, most of you guys are getting it right. Okay, so when we talk about at least 10 free throws, we've got n is equal to 11, p is equal to 0.93, and x is going to be 10 or 11. Okay, so now we have two calculations to do. We've got one where we've got to do 11 choose 10 for the number of arrangements times, and we need to make the basket, we need 10 makes or 10 hits, so I'm going to have 0.93 raised to the 10th times 0.07, which is the probability of missing one, and we'll put that to the 1 right there. Okay, and so when we do this calculation, I'm going to get basically 11 choose 10. This comes down to, this is 11, and then this part multiplies to 0.03388, and so when we multiply this together, I get 0.37267. So this is the probability of making 10 out of 11 free throws. 10 out of 11. Okay. The other part will be 11 choose 11, and then we're going to multiply this times 0.93 raised to the 11. Okay, now 11 choose 11 is just 1, and we could have just said, well, this is kind of good old probability. I have to make a free throw with probability 0.93, raise that to the 11th power, and get our answer. And then we would also have, we could do 0.07 to the 0 to indicate that we're going to miss 0 times, and this comes out to be 0.4501. So we add these two together to get the probability of 10 or 11 is going to be, we add these two together, 0.37267 plus 0.4501, and we get this. So there's a pretty good chance he'll make at least 10. Okay, but that also means there's about a 18% chance that, you know, he misses more than 2, which or misses 2 or more. And when you're watching a game, that, you know, that feels like, oh my gosh, what's going on? But that's what we have. Okay. All right. So, kind of putting all of this together, we can create a formula, kind of for the binomial probabilities. Probability formula. Okay, so, you know, identify n, p, and x in the problem. So when you go through a binomial problem, you got to identify n, p, and x, and then the probability of getting x, okay, of x successes, okay, which we often just write the probability of x, is going to be n choose x, okay, we can write it this way, times the probability of a success. That has to happen x times, and we're going to multiply it times 1 minus p. This is the probability of a failure, and how many times does that have to happen? It has to happen n minus x times. Okay, so this is n choose x. This is the number of possible arrangements. Okay. This is p raised to the x. This is the probability of success p. Okay, and it has to happen x times. So we have p to the x, okay? And then over here, 1 minus p is the probability of a failure. Okay, and that has to happen n minus x times. Okay, if we have a total number of n trials, then and x of them are successes, then the rest, n minus x, have to be failures. Okay, has to happen n minus x times. So we have 1 minus p raised to the n minus x. Okay. Does that seem good with everybody? Okay. And you know, sometimes our questions get you know, a little bit trickier, right? So we could turn things around and we could say, you know, what is the probability that after 11 free throws, or that in 11 free throws, Steph Curry misses twice or more. Two times or more. Okay. Now, in this scenario, we would have to figure out, okay, if we say n is 11, and then p could be makes the basket with 0.93. This is making the basket. Then our x is technically 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Because missing 2 or more times includes all of these outcomes. Okay. Now this is 10 calculations. That's probably too many to do. Okay. We would have to do probability of 0 plus the probability of 1 plus the probability of 2 all the way up to plus the probability of 9. Okay. This is, you know, too many calculations. So what's a better alternative? Yeah, we could. This is equal to 1 minus the probability of 10 plus the probability of 11. Does that make sense? Because when if you shoot 11 free throws, okay, either the basket is going to go in there 11 times, 10 times, 9 times, or 8 times. These are all of the possible outcomes. Okay, there's no other possibility as far as how many baskets you make. Okay, this covers all of them. And so if we want everything from 0 to 9 added up, instead of having to do all of the calculations for 0 to 9 and add them up, one option is I can just do the calculations for 10 and 11, add those up, and subtract that from 1, because one of those possibilities has to happen. Okay, so that's the binomial distribution, and you guys have a quiz on it tomorrow. So good luck.